We present a fast frequency domain solution to on-the-fly modal synthesis to simulate sounds from objects falling and colliding as shown here. We can also process scenes with both recorded and modal sounds by introducing a scalable pipeline complete with auditory masking and sound source clustering. The key idea of our approach is to exploit the sparsity of modal sounds in the Fourier domain. As we can see in this spectrogram of a mode, few frequencies contribute to the signal. To achieve frequency domain modal synthesis, we propose a fast approximation to short-time FFTs for modes. Time domain modal synthesis requires 1024 operations per mode per frame. In our approach, we simply add a few frequency coefficients per audio frame, giving a speedup of 5 to 8 times. To avoid reconstruction artifacts, we blend overlapping frames using a window function. Reconstructing with the hand window, we see some error at the sound onset or attack, but excellent reconstruction elsewhere. A rectangular window reconstructs the onset better, but results in audible aliasing in remaining frames. We choose the hand window to guarantee good reconstruction and to combine with recorded sounds. However, the attacks have degraded quality. To improve attack reconstruction, we subdivide the first frame into 4 subframes. The first half of the first subframe uses a rectangular window, followed by a hand window. 2 hand windows follow, and the last subframe contains a square root of hand window to ensure blending with all other frames. We integrate our new modal synthesis method into a scalable audio processing pipeline, combining recorded and modal sounds. This requires us to sort modal sounds. We sort modal sounds by decreasing energy, estimated using scalar products. We exploit the fact that energy is concentrated in a small number of modes, shown in the upper left. We use this scene, which contains 4 different object types and 4 different materials, to evaluate the error of our approximation. The error for the test scene is shown here. Neuroscience research shows that we perceive visual and auditory events as synchronous even when audio lags by up to 200 milliseconds. We use this result for temporal scheduling by delaying audio processing. In red, we see computation load before delay. In green, we show our temporal scheduling result with a delay of up to 200 milliseconds. The abrupt peak is now shorter and smoother. We first compare to time domain processing using all modes. We next compare to a mode culling time domain approach. We performed a perceptual test to evaluate quality of our approximation by varying the cost of the approach. For this scene, and an 8000 bin budget, quality is rated at 75% of the quality of the hidden reference. We next show a set of interactive sequences, all recorded in real time, directly off a dual-core PC.